your quiz says estimate the area under the curve between lower bound a is equal to -2 and upper bound b is equal to 0. And you're going to use 2 rectangles to estimate the area, and then 4 rectangles, and then 8 rectangles to estimate the area. So this is a Riemann sum type problem. So if you're just asked to estimate, then this is talking about a Riemann sum. And the way that this looks, hopefully you remember from last time, still the way that this looks, is this curve, e to the negative x divided by x minus 1 plus 5. That curve looks like the red curve in this Desmos thing. So it looks like that red curve. If you were going to estimate the area between x equals -2, that lower bound, and x equals 0, which is that upper bound, if you're going to estimate the area with 2 rectangles, the way a Riemann sum works is you make the height of the first rectangle equal to your function evaluated at -2, and the height of the second rectangle is going to be equal to the function evaluated at -1. The width of these 2 rectangles is both going to be half of the interval, so the width is 1 for each rectangle. And basically you add the areas of these 2 rectangles, and that's your estimate of the area under the curve. And kind of like we saw last time, if you increase the number of rectangles, that estimate that you get should get closer and closer to the actual area under the curve. And if we have like something like 50 rectangles, then it gets really, really, really close to the exact area under the curve. But in our case, we're going to evaluate that with 2, 4, and 8 rectangles, so we're not going to get super close to the correct area. But that's what we're doing. So in the case with 2 rectangles, like I said, we're going to have one rectangle with height, we'll call it height 1, and another rectangle with height 2. So the area of each rectangle is the height times the width. And height 1 is going to be my function evaluated at -2. And if I plug in -2 here, I guess you would need a calculator. Not pass up calculators. You would do e to the power -2 divided by x minus -2 plus 5. So e to the power -2 would be e to the power 2 divided by x minus -2, that's x plus 2, and then plus 5. So somebody in your calculator do e squared divided by x plus 2 plus 5. Don't know what that first height is. If you do that right in your calculator, it should be something like 2.537. Looks like that's the height of the first rectangle. 2.537. And the height of the second rectangle should be your function evaluated at -1, and that's going to be e to the power -1, so e to the 1 power, divided by x minus -1, so x plus 1 plus 5. That's an h. So the height of the second rectangle should be 3.641. And so the area, estimating using 2 rectangles, is going to be the height of the first one, call it 2.5, times the width. And the width of these rectangles is just 1, right? Because I have an interval from -2 to 0 that has an interval width of 2. I'm estimating with 2 rectangles, so 2 divided by 2 is 1 for each rectangle width. And then the height of the second rectangle was like 3.6. So just keeping two significant figures, this would be like 6.1 for my estimate. So that was with 2 rectangles. If I try this again with 4 rectangles, let me try. N is equal to 4, then my area is going to be the sum of 4 different rectangles. I'll call it h of 1 plus h of 2 times the width plus h of 3 times the width plus h of 4 times the width. And my width this time is my interval length 2 divided by my number of rectangles. So 2 over 4 is half for the width of each of those 4 rectangles. The height obviously varies. So the height of the first one is again my function evaluated at -2. It's the left side of the first rectangle. Now the height of my third one is going to be your function evaluated at -1, because this would be where your third rectangle has its left side. So the left side of the third rectangle would be at the point x equals -1. So for the second rectangle, the left side is going to fall on x equals -1.5. And then for the fourth one, the left side of the fourth rectangle falls at x equals -half, right here. Then when you actually plug those values, -2, -1.5, -1, -half, plug those values into your function. It's basically where this red curve is. You should get the values, well, the same 2 values we got before, and then 2 new values for the second and fourth rectangles. So the first one should be 2.537. The third one should be 3.641, because we've actually figured those out already in the n equals 2 case. The second one has height 3.207. And then the fourth one would have height, whatever you get from plugging -half into this function, and that is going to be 3.901. So for my area, we could actually factor out one of those widths, right? And so my area could be just the width of a rectangle times h1 plus h2 plus h3 plus h4. So I could actually just add up these 4 heights and then multiply by 1/2. And whenever I add up all those heights and then I multiply by 1/2, I should get a Riemann sum of about 6.6. And the last thing you would do is, for the case when you have 8 rectangles, you would have to find rectangles with the width of 1/4. The width is 1/4 because you have an interval from -2 to 0, so an interval with width 2, but then you're dividing up that width into 8 different rectangles. So 2 divided by 8 would be 1/4. The width of each of these 8 rectangles is going to be 1/4. And your number of rectangles being 8, your width being 1/4, the area of your Riemann sum, adding up the sums of all 8 rectangles, that's then going to be the width, 1/4, times the height of the first one, plus the height of the second one, plus the height of the third one, plus the height of the fourth one, plus the height of the fifth one, plus the height of the sixth one, plus the height of the seventh one, plus the height of the eighth one. And remember the height of the rectangle every time. In order to find the height of a rectangle, like rectangle number 5, no, let's make it rectangle number 6 to make it interesting. The height of rectangle number 6, 1, 2, 3, 4, 5, 6, would require you to go to the left side of rectangle number 6 at -3/4, x equals -3/4. Plug in x equals -3/4 into our function, to get a value of 3.79, and that would be the height of like rectangle number 6. All you would have to get to do again is, instead of x in this function, plug in -3/4. And that's how you find the height of the rectangles. You actually plug back into the original function there. And doing this, we would end up with a Riemann sum of 6.9-ish. And the big idea from yesterday, the really important thing to take away from last Thursday, was that we could actually find truly the area under this curve if we chose enough rectangles. But it couldn't just be 8 rectangles or even 16 rectangles. It would have to be something like 800 rectangles, right? If we use lots and lots and lots of rectangles to estimate the area, then we can actually get very, very close. And so, I don't like how that label is messed up. I'm going to fix it. Boop. Okay. Anyways, with 800 rectangles, we get a Riemann sum of 7.04 something, and that gets very, very close to the actual area. And in fact, like I mentioned, the way that Desmos is calculating the actual area is actually just counting up the areas of rectangles. It's doing a Riemann sum, but it's doing it with even more than 800 rectangles. It's doing it with a lot of rectangles to get the actual area number. Anyways, this relative error between the Riemann sum and the actual area goes to 0 as n approaches infinity. And if we are actually taking the limit as the number of rectangles goes to infinity, or you could say taking the limit as the width of the rectangles goes to 0, we would write it like this. We would write the definite integral between -2 and 0 of my function is 7.04-ish. And you can just look at our estimates with 2, 4, and 8 rectangles. With just 2 rectangles, I got an area of 6.1. Then when I used 4 rectangles, I got 6.6. When I used 8 rectangles, I got 6.9. And so you can tell we're getting closer and closer to the actual area. Y'all have any questions about this before we move on and talk about today?
Would it be okay to write that ish on our test if that question pops up?
Yeah, well, I mean, you know, I write ish because it wasn't exactly 7.04. It was like 7.0427221, and that decimal expansion would continue. I think it's an irrational number, so there would be infinitely many decimals in the decimal expansion of that number in reality, but that's why I write the ish.
Yeah, put simply 7.04.
Yeah. Okay, so hopefully today is more entertaining and more like, oh wow, that's so cool, and not confusing. At any point, if you're feeling lost, you can stop me, and I would be really happy to answer questions. Because like I said, I just don't want you to get lost today in all the details. The big idea is about what we call the fundamental theorem of calculus, and you'll see this a lot of places. They break up the fundamental theorem of calculus into 2 different mini sub-theorems, if you will. Whenever we're talking about a function f of x, in this class, I'm going to use the notation capital F of x to represent the antiderivative. So I'll just make, you know, the little letter that represents the function, I'll make it a capital if I'm talking about the antiderivative, as a general rule. Maybe not all the time, but this is something that we commonly do in calculus. So we're supposing capital F is an antiderivative of lowercase f. Then if you just choose any constant k, doesn't really matter. As long as k is a number, a constant number, then you can say that f of x is an antiderivative if it's equal to one of these definite integrals we just learned about, with lower bound k and upper bound x, where the curve, where we're finding the area under the curve, is that lowercase f function. So I'm going to explain this here in a second. I'm just trying to show you what we're about to work up to. And if you let capital F be a specific antiderivative of f, then you have to choose a specific value of k that matches that specific antiderivative. If you're confused so far, that's okay. Just hang with me for a minute. If you want to go in reverse, if you want to say, I have this definite interval, and I want to evaluate that definite integral exactly, not meaning like I'm going to take a Riemann sum with like 16 rectangles, but I want to know exactly the value of the area under the curve, you can solve this in actually a lot smarter way than computers can. You don't have to add up rectangles. What you can do instead is take the antiderivative of that integrand function and then evaluate that antiderivative at the upper bound and lower bound of your definite integral, subtract the two, and the difference of those two values is the area underneath the curve. And so you can do that as a human. Most computers can't, right? So like your calculator will claim that it can evaluate definite integrals. Desmos claims that it can evaluate definite integrals. But they can't really. They're just basically adding up a bunch of areas of rectangles. They're basically just doing a really advanced Riemann sum. You can do a step better. You can evaluate those directly by using this antiderivative formula. So the next few pages in your notes are explaining why this works. Like, why are these things true? It should sound a little bit ridiculous. But we're asking first about the number one part. Why would this equation be true? And keeping the equation balanced, we're going to take the derivative of both sides. So on the left side, we have the derivative with respect to x of the antiderivative of the function f. And on the right side, we'll take the derivative with respect to x of the definite integral that we're talking about. So on the left side, since capital F is just an antiderivative of f, then taking the derivative of the antiderivative just gives you the function itself. And then on the right side of this equation, the derivative, that d over dx operator, remember that the lowercase d's represent small changes. And so when you take a derivative, you're saying, for a given small change in my independent variable x, what kind of small change would be introduced in the function we're talking about? And then to talk about the derivative, we talk about a ratio between that small change in the function divided by the small change we introduced in our independent variable. So dx represents a tiny change to our independent variable, and this numerator, this d, all of that junk, this represents a tiny change in that integral. And those tiny changes are associated because whenever you make a tiny change in the x value, it causes, or it elicits a corresponding tiny change in the value of the integral. Because if x increases by just a little bit, then the upper bound of that integral increases by just a little bit. So you expect the area under the curve to increase by just a little bit. And then again, when we take the derivative, we're talking about a specific ratio where I divide that tiny change by that tiny change. So whenever we allow x, my independent variable, to grow by just a little bit, we add just a little tiny change plus dx to it, I would write my upper bound of my integral as x plus dx, x plus a little extra. And the way that definite integrals work, since a definite integral is talking about some area under a curve, if I wanted to take the area under this curve between lower bound k and upper bound x plus dx, that would be the same as if I took the area between k and x and then took the area between x and x plus dx and then added those two areas together. And that's what I mean by this formula right here. The area under a curve between k and x plus dx is just equal to the area under the same curve between k and x plus the area under that curve between x and x plus dx. Does that make sense? Okay. So this is my original integral, that integral from k up to x. So really, what happens whenever I introduce the change x plus dx is this. This is the additional little bit that I get from x growing by that plus dx. And so on the next page, I'm going to focus on this third integral, the one that gives me the area under the curve between x and x plus dx. That's how much my numerator is growing whenever I'm trying to take the derivative. When we ask d of all of this stuff in the parentheses, that is actually the same thing as this because of our little argument that we've constructed so far.
So, okay, wait, I do have a question. You know when we have x, would that be like our minimum, and that's where it changes? Is that right? Or is it just random? Like on the little picture you showed us?
Yeah. It doesn't have to be at the minimum of the curve. It could be anywhere. I mean, this works for any curve at all, right? Any curve you can imagine. Like that curve, you could have this value for x. And so this would be the area under the curve between k and x, and this would be the area under the curve between x and x plus
So
dx.
we're just finding it between the two like rectangles pretty much.
Yeah. Yeah. It's not important what x is. It's not important what k is. It's not even important what type of curve we're talking about. I'm just making a really abstract argument saying, imagine some curve, imagine some point k, imagine some point x, right? The exact values aren't important. It's kind of like Cyrus pointed out, there's no numbers. There's no numbers in this math. Yeah. Okay. So now again, like I said, on the next page, we're focusing on just this little bit. This is the change in the value of my definite integral that's associated with a little change in x that we call dx. So we can approximate this integral right here from x to x plus dx using a certain rectangle. That's going to be a rectangle with height f of x. F of x is representing the type of curve I have. And then it's going to have width of dx. So we have height times width. And to sort of visualize this, the width of this little orange rectangle is in the x direction. So I talk about that width as being a small change in x. So I'll call it dx for the width of this rectangle. And then the height of this rectangle is just taking this function, this blue curve representing y is equal to f of x, and this height is going to be my function evaluated at the point x. So this little orange rectangle, this would be f of x times dx as the area. And I also want to point out, though, that there's a little bit of area under the curve that's not covered by the rectangle. So just like yesterday, if you were to zoom in really close, you look at this little additional bit above there. Yeesh. So this integral from x to x plus dx has this little extra bit that's not actually covered by this rectangle. So it makes that rectangle an approximation of this definite integral, kind of like we did with the Riemann sums. The rectangles don't perfectly match the area under the curve. But what I'm going to show you is that if we take the limit as this dx width goes to 0, so we squish it smaller and smaller, it turns out the relative error of this certain approximation, of approximating that area using a rectangle, the relative error goes to 0. And so if we allow us to take the limit as dx approaches 0, then this approximation becomes a fact. It's no longer just an approximation if the error of your approximation is 0. And let me try to animate this just a little bit. So again, the blue curve is given by y equals f of x. Let me just show you if I take the orange out for a moment. This blue little bit, that's the additional area of my definite integral that I get when I add dx to my x value. So this vertical blue stripy line would be my x value, and then the difference between this black stripy line and the blue stripy line would be like my dx with my additional little bit that I'm adding to x. And so as I let dx become larger, that gives me more area, and as dx becomes smaller, it gives me less area, right? So I even have a calculator. It says area added by dx, and it's some small amount. And it also can tell me if I choose to approximate that area using this orange rectangle with height f of x and width dx, I'm going to have some approximate. So I say area approximated by that rectangle, and it's pretty close, but not exactly the same as the area added to my definite integral because of this little sliver. But notice, calculating the relative error means that I divide the difference between these two by the true area. So I divide blue minus orange divided by blue, and that gives me about 5%. As I allow the dx, or as I allow the width of that rectangle to shrink to 0, my relative error also shrinks to 0. Ooh, spooky. So, this is really, really tiny, but if I give it an even tinier number, so I let my dx width be like that, notice the relative error just vanishes. My approximation is going to be equal to the true area in the limit as dx goes to 0, and I let that be a super tiny number. Okay. So we're going to just call this an equivalence, because I'm going to say that dx is going to approach 0 in the limit. And so what I can write instead of writing this change in the value of my definite integral associated with the dx change, I can write the area of that rectangle approximation, f of x times dx. And we'll just assume tacitly every time you see dx, we're talking about the limit as dx approaches 0. But if I have dx divided by the same dx, those cancel out, and I find that I have the equation that my lowercase f is equal to my lowercase f. So we're talking about the same function. And this is exactly what we wanted to find. It shows that if we start from that fundamental theorem of calculus idea number 1, and we sort of analyze it a little bit, we reason about it, using geometry, and we take a limit, we realize that this is consistent. Our ideas are self-consistent with each other. If we had assumed that that idea number 1 was not true, and we tried to prove that it wasn't true, we would run into a contradiction if we tried to follow the same line of reasoning. And so if this were a true rigorous proof, I would show you a proof by contradiction, but it's better to teach this the way we've done it, where we just show that these two functions are equivalent. I know that was a lot of explaining in pictures. Do y'all have any questions about why this is true? I know it might take a couple of times seeing it, but all we've done so far is I've said this is true and here's why.
So you have these videos
Mm-hmm.
on chemistry just to re-watch.
Yeah, this is getting recorded right now, and I'll post it later. There's also people on YouTube that can explain this even a little bit better than I can, because if you're like on YouTube, a lot of them are good at like animating stuff. Let me just show you on YouTube where you would look if you want to get a really good explanation. Let me do 3-1.
Don't we get like Khan Academy free since we're college students?
Everybody gets Khan Academy free.
Never mind.
Yeah.
Yep. Well, I'm still right.
Yeah. Let's see. So there's this channel called 3 Blue 1 Brown, and he makes good videos about math. A lot of them are about pretty advanced math, but his series about the essence of calculus is not that advanced. Like, you could probably understand all of these videos really easily. And if I could just find the playlist. Here we go, okay. This is the playlist. And we're looking for, and by the way, you might check this out anyways, just because he has videos about derivatives, and has a video that explains what's so special about Euler's number, the 2.71828 number. He has a video about implicit differentiation, so if you want to see a little bit more of an intuitive explanation of implicit differentiation, he has some cool animations about that. He's got a video about limits. And then okay, here we go. This is what I was looking for. He has a video about integration and the fundamental theorem of calculus. And it's like a 21-minute long video. But again, if you have time, or if you feel like you're struggling to understand stuff, this is a really good playlist that I would check out. So it's called Essence of Calculus by 3 Blue 1 Brown. Okay. Anyways, now we're going to move on to number 2. And so number 2 is going to be the most useful part of this fundamental theorem. And number 2 is about evaluating definite integrals. So let's jump over to number 2. Actually, I have one more thing to say, apparently, about this that I put in the notes. Whenever you see this, we call this an accumulation function. So on the right side of the equation, we have the definite integral from a lower bound, which is a constant number for my lower bound. And I let my upper bound be a variable, my variable x. Whenever you have a variable upper bound, we call this an accumulation function, because if we have the function lowercase f, and it represents the rate of like water flowing into a bucket, so it might be in like gallons per minute, maybe, then your capital F is going to tell you how much water has accumulated in your bucket between time t is equal to k, that constant, and whatever variable you choose for your upper bound, right? And so probably in this situation, k would be 0, so you have a lower bound of 0, and you just start the stopwatch when you start filling up your bucket. And then even if the flow rate of the water varies over time, you could still calculate the volume of the water in the bucket at any time after you start filling the bucket using what we call an accumulation function. And we also have this lower bound k, and we never really stated what k was in the proof, and it didn't really seem to matter what k was. But remember when we took an antiderivative? taking the antiderivative of like x gives you 1/2 x squared plus c. C was kind of an arbitrary constant. Now this k is kind of an arbitrary constant. And I can set these two things equal to each other because inside this antiderivative, I have a plus c somewhere. And in this definite integral, the fact that I can change my lower bound of my integral gives me the flexibility to change that plus c. So if you choose a different k, you choose a different plus c. If you choose a different plus c, you choose a different k. Those are both sort of arbitrary constants that are going to be linked to each other in whatever problem you're working on. So, full circle there. Okay. Now, like I said, this is really the useful part of today's lesson, this definite integral formula. And so, thankfully, this proof is a lot shorter. If we use the fact that my antiderivative evaluated at b would be the integral from k to b of my function lowercase f of t, that's actually just based on what we've already proved. That's based on idea number 1 from the fundamental theorem. I can do the same thing with my antiderivative evaluated at a, just make a the upper bound. And if I subtract the two, then f of b minus capital F of a is going to be equal to this definite integral minus this definite integral, because I'm doing capital F of b minus capital F of k. And let's now think a little bit about the right side of this equation here. So I'm going to let this be k, and this is going to be a, and this is going to be b. I'll just throw in some curve. Could be anything, but it's going to be y is equal to f of x. Now, this area between k, a, the x-axis, and the curve, this area is the orange underlined definite integral, isn't it? Because I've got lower bound k, upper bound a, and you know that the definite integral gives you the area under the curve. Okay, what about this definite integral from k up to b? Well, then that integral from k up to b would be this whole area under the curve between k and b, right? Based on what definite integrals calculate. And if I really just want the area between a and b, so let me get out one more color. I'll call this my purple area for this definite integral. This would be like the purple zone, the area with lower bound a and upper bound b underneath my curve f. Well, this purple area is just equal to the blue area minus the orange area. So blue area minus orange area, this whole right side of the equation can be simplified to this. And after that sort of geometric logic, we get exactly what I wanted, which is to say that you can evaluate this integral from a to b of some function by just taking the antiderivative of the integrand. Evaluate that antiderivative at the upper bound b, and then subtract capital F evaluated at the lower bound a. Now, I know there's just so much conceptual stuff going on. Hopefully I can make it to some examples before class is over. If not, we'll pick it up on Thursday, wherever we have to leave off. But there's one important detail that we've kind of ignored so far, because so far we've been only talking about areas above the x-axis underneath the curve. But if you have an area above the axis that's bound between a curve and the x-axis, it counts we would say it counts positively towards the value of the definite integral. But if you have your curve that dips below the x-axis and you calculate an area using a definite integral below the x-axis, that's going to count negatively towards the value of your definite integral. And you can imagine this works with Riemann sums too, because in a Riemann sum, you would have, your x-axis, and like I said, we're going to talk about some curve that dips below the axis. And so with the Riemann sum, the area is just the height of a rectangle times the width of the rectangle plus the height of a rectangle plus the width and so on. Sorry, times the width. And so on, the areas of all the rectangles. Well, a Riemann sum here would look like adding up rectangles that look like this. But since we're dipping below the x-axis, the height of these rectangles would be at negative y values. And so you would say that these rectangles have negative height. And so all of these areas of the rectangles would be like negative areas, right? Well, in our case, you might mark on your notes which areas are red and green because it printed in black and white whenever I printed your notes today. But basically, in this curve, 1/2 x cubed minus x. The area in green, which lies above the x-axis, is going to count positively. And that area in green is actually an area of 1. If you add up these two areas, these sum to 1. Also, if I add up these red areas, these sum up to 1. So you might see that the total shaded area was 2, because 1 plus 1 is 2. But the value of the definite integral is going to count the red as being negative and the green as being positive. And so the definite integral is going to give me a value of 0. Let me try to just show you one more time with Desmos what we're doing here. So here we go. If I start off and my lower bound's in the red and my upper bound's in the red, notice I have 0 green area, I have some red area, and so the value of my integral is going to be negative. Because I've got no positive area, only negative area. Whenever I start going into the positive section of the integral, notice the value of my integral is going to start to get closer to 0 because it's a negative value and I'm adding positive area to it, so we're getting closer and closer to 0. If I get rid of my negative area and I only look at positive area, the value of my integral is going to be a positive 0.47. If I start to add more negative area to it, the value of my integral goes down as I'm adding more negative area. And then it's going to start going up again as I add more positive area. So basically, if you have a question about the total area bound between a curve and the x-axis, that's not necessarily as easy as just taking your definite integral. In general, what you would have to do is you would have to factor your polynomial to find the zeros of your function, and then you would have to take the definite integral between the zeros, and then you would have to make any negatives into positives, just take the absolute value, and then you would want to add all those up together. So it kind of gets to be a pain in the butt if you have a trick question about sort of the area bound between the x-axis. But I want to mention it to you because it's important to see how the value of an integral and the total area between a curve and the axis are not exactly the same thing in every case. If you're only talking about areas above the axis, then the value of the integral and the shaded area do match. Okay, so some examples. And that's good. We actually still have 17 minutes for examples. So example 1 says, what are the zeros of my function 1/2 x cubed minus x. And so this is just algebra. You'd probably say, let me take out a greatest common factor. And so I'll factor out an x. So I have x times 1/2 x squared minus 1. And now I need to factor x squared minus 1. Well, 1/2 x squared minus 1. And I know, based on just algebra, that I could write this as x minus one of the roots times x minus another root times 1/2. And I know if I'm trying to find the roots of a polynomial, I can just write that polynomial equals 0 and then try to solve this equation, right? So I'll add 1 to both sides and get 1/2 x squared equals positive 1. Multiply both sides by 2 and x squared is equal to 2. And when I take the square root of both sides, I should write x is equal to plus or minus square root 2. So I could factor this as 1/2 x times x plus square root 2, 2, and x minus square root 2. And if that's true, if that's my factorization of this polynomial, then it looks like I have 3 zeros of my function that come from my 3 non-constant factors. So I have these 3 factors, and one of them tells me that my whole function is equal to 0, or y is equal to 0 whenever x is equal to 0. If x is equal to positive square root 2, then my third factor would be 0, and that would make the whole thing 0. And if x is equal to negative square root 2, then this middle factor would be 0, and that makes y 0. So the zeros of my function are at 0, negative square root 2, and positive square root 2. And since this is the same function, you can see I have my function crossing the axis at x equals 0, at x is equal to positive square root 2, and over here at x is equal to negative square root of 2, right? So those are the zeros of my function, both graphically and using algebra if you don't have a graph. So example 2 says, evaluate the following definite integral. And we're going to rely on that fundamental theorem of calculus rule number 2, where we're saying if I want to evaluate a definite integral, I'm going to call my integrand lowercase f, and this is now just a matter of finding the antiderivative of that, evaluating the antiderivative at negative square root 2, my upper bound of the integral, and then subtracting the antiderivative evaluated at negative 2, because negative 2 would be the lower bound of that definite integral. So if my lowercase f function is 1/2 x cubed minus x, what would be the antiderivative of that function? What's the antiderivative of 1/2 x cubed? So close, you just took the derivative, not the antiderivative.
Oh.
Yeah, it's going to go up from x cubed to x to the 4th, and then it should be 1 over.
No, not adding.
By your exponent. Isn't it?
Wouldn't it be 4 divided by 2? No.
Yeah. When you do the antiderivative power rule, you add 1 to your exponent, and then you divide that term by your new exponent. So we just went up from 3 to 4, and then we divided 1/2 by 4, and 1/2 divided by 4 would be 8. Sorry, 1/8. 1/8, yeah. 2 times 4 is 8, so that would be 1/8. And divide by 4. Okay, and then the antiderivative of negative x is going to be negative what?
1/2x squared.
Perfect. Yeah. So we added 1 to our exponent, we got x squared, and then we divided by our new exponent, so we divided by 2, and that's where the 1/2 came from. Okay, then we write plus c because it's an antiderivative after all. Now, this definite integral is equal to this antiderivative function if I evaluate it at negative square root 2 and minus that antiderivative function evaluated at negative 2. So plugging in negative square root 2 for x here is going to give me 1/8 times negative square root 2 to the 4th power minus 1/2 times negative square root 2 squared. And then for this next part, I want to subtract that same antiderivative evaluated at negative 2. So I subtract 1/8 times negative 2 to the 4th power. And then minus makes a plus 1/2 negative 2 squared. And I forgot something. I forgot plus c here. Oops. And then I also forgot plus c over here. But I'm subtracting this antiderivative, so that plus should be a minus, since it's all getting subtracted. And then notice if I add plus c and then I subtract plus c, then those c's cancel. I'm going to repeat that one more time, just because I think this is an important thing to notice about your very first definite integral problem. Right now I'm dealing with my capital F of negative square root 2. And so I've plugged in negative square root 2 for x in my antiderivative formula. And then I'm going to subtract that same antiderivative if I evaluate it at negative 2. So I'm going to subtract 1/8 times negative 2 to the 4th power minus 1/2 times negative square root 2. Negative 2 squared plus c. Okay, now at this point, I'm going to distribute the negative sign to all this crap inside the parentheses. So I'll get 1/8 negative square root 2 to the 4th power minus 1/2 negative square root 2 squared plus c. Now distributing that minus sign, and it's really important that you distribute this minus sign properly or you won't get the problem right. You do minus 1/8 negative 2 to the 4th. Minus a negative makes plus 1/2 negative 2 squared minus c, because you distribute the minus sign. Then like I just said a moment ago, I have a plus c right here and I have a minus c. But plus c, minus c means these cancel out. And it turns out this is always the case. If you're evaluating a definite integral, you end up having the antiderivative of the upper bound minus the antiderivative of the lower bound. And since it's the same antiderivative, whenever you subtract the two, that plus c on the end always cancels out. So for a definite integral, you never have to specify what that c value is. That's not true for all antiderivatives in general. It's important to remember that for antiderivatives. But as long as you're only working in the context of a definite integral problem, one with a lower bound and an upper bound, then you can forget about the plus c. Okay.
So we just take those out, and the rest is the answer.
Yeah, so
After simplifying.
yeah, we're going to simplify this a lot. So this is 1/8. The negative doesn't matter because something negative to the 4th power, well, even powers get rid of negative signs. Yeah. so that's going to eventually not matter. Square root 2 to the 4th power is going to be 4, because square root 2 times square root 2 is 2. 2 times 2 is 4. Then I have minus a half times 2 minus 1/8 times, again, the negative doesn't matter. 2 to the 4th power is going to be 16 plus 1/2, and then 2 squared is 4. 4 divided by 8 is 1/2, minus half of 2 is minus 1, minus 16 over 8 is 2, plus 4 over 2 is 2. So the 2's cancel, and this should be negative half. So you're right, we do have to simplify a whole bunch.
Just
Yeah.
to make sure.
So we just found that the definite integral evaluated between negative 2 and negative square root 2 is negative half. Let's check with my little calculator to make sure that makes sense. So I have the same function in blue here. And if I take the lower bound to be negative 2 and the upper bound to be square root of 2, well, actually negative square root of 2. Huh. That's really weird. I feel like that's not working. Hold on. It's just not updating my little graph. Let me try this again. Desmos is like broken completely right now. This has never happened to me. What in the world? There we go. Perfect. Okay. Negative square root 2. Man, it is slow. This is acting really weird.
Whoa. That's totally what you meant to put on it, right?
Nope.
Oh wow.
Something really strange is happening here. Oh, I know why. And I don't know how that happened either. Somehow a lot of those things got checked that shouldn't have been.
It's the equation now?
Ha! And it's back. Okay, let's see if it works now. Negative square root 2. Ha! Did it. Okay, so this area in red is half. And of course, since it's a red area, it's below the axis, then the value of the definite integral should be negative half, which is confirmation that we just did our example correctly. Okay. Took Desmos a while. But that was example 2. Where that was example 2. This is example 3. And we want to take the definite integral, but notice it has the same integrand as we had for the previous problem. And since it has exactly the same integrand, the same chunk on the inside, that means the antiderivative is the same. And so we just need to evaluate that antiderivative at the upper bound and then subtract the same antiderivative evaluated at the lower bound. And you've actually already figured that out, the antiderivative at the lower bound here. So the first part, antiderivative evaluated at 0, would be 1/8 times 0 to the 4th power minus half times 0 squared plus c. And then we subtract 1/8 times negative root 2 to the 4th power minus 1/2 negative root 2 squared plus c. Okay. Now when we go to distribute the minus sign, and we can go ahead and clean all those zeros up because 0 times anything is 0, we can write c minus 1/8. Negative root 2 to the 4th power is going to be 4, and then minus a negative makes a positive, and then this is minus half times negative root 2 squared, which is just 2, so half of 2 is, well, let's write half of 2, and then minus c. So again, the c's always cancel. I didn't even really have to write the c's because I knew that they were going to cancel. But this is negative 4/8, which is negative half, plus half of 2, which is 1, so that's positive half. So this definite integral, in example 3, if you do it correctly, you should end up with positive half. And let's see if Desmos is broken or not. We're going to set my upper bound equal to 0 and my lower bound equal to negative square root of 2. And so we're talking about this area between negative root 2 and 0. And it tells me that my area and the value of my integral should be positive half. And that's what we calculated was positive half. Example 4 has us calculating the area, or rather calculating the definite integral between 0 and positive square root 2. So let me make my upper bound positive square root 2 and my lower bound 0. And my answer should be, if I did it right, negative half. And finally, if I make my upper bound 2, my lower bound square root 2, I should have a value of positive half. So for my next few examples, this value should be negative half if you do it correctly. This value should be positive half if we do it correctly. So evaluating this particular definite integral is going to require my function evaluated at 2 minus my antiderivative function evaluated at negative 2. And so this would be, what is it, 1/8 times 2 to the 4th power plus half times 2 squared plus c minus 1/8 times negative 2 to the 4th power plus 1/2 negative 2 squared minus c. Of course, the c's cancel each other out, so I don't need the plus c. An 1/8 of 16 is 2. A half of 4 is 2. Negative 2 to the 4th power is like 2 to the 4th power. It's like 16, so that's like minus 2. And then negative 2. Wait, is it minus 2? 16 divided by 8.
Wouldn't we use minus signs? Or for the... For 1/8 minus 1/2. I think I did get...
Yes, you're right. I think I see my mistake. You were right. There we go. Thank you, Deanna. That actually really helps because I was about to get the wrong answer. So thank you for that help. The 4th term, 1/2 of negative 2 squared. That's like 1/2 of 4. So that's plus 2. And then 2 minus 2 minus 2 plus 2 is 0. So my definite integral is 0, like I promised it should be.